Welding and Chemistry, Gary Pace, PE, CWI, April 2019. Kind of take a run at talking about welding and chemistry and the periodic table and see if we can, I don't know, if this rambling rant turns into anything useful, but we'll give it a go and see where this ends up. Okay, I know it gets tedious. I include one of these in about every other um, presentation I do, but I guess I just want to spread the wealth. Acknowledgments, I poach a lot of this material from the Nuclear Regulatory Commission, Introduction to Welding Technology and Code courses, ML 12157, A587. It's a good starting point. Can teach the Canadian deuterium uranium people. HTTPS, I'm not going to read that web page. You guys can figure it out, the can do stuff. The U.S. Army's also got a pretty good, it's old, but it covers a lot of material. TM 9-237, Welding Theory and Application, is a good place to find some high quality welding information. None of it's changed over the last 50 years, but anyways, that's why I always include this, is because there might be somebody out there that's looking for some free material, doesn't want to pay for a book, and you want some good high quality welding material. This is it. Here's a list of alloying elements and their effects. You've got austenite formers, nickel, manganese, carbon, nitrogen, copper, and cobalt. You put these guys in an iron alloy, and they're going to form austenite. Ferrite formers are aluminum, titanium, vanadium, chromium, molybdenum, niobium, and silicon. So depending on what your mix is, what the percentage of the alloying elements are in the alloy, is going to tell you what you get as far as a microstructure. Is it going to be ferritic? Is it going to be austenitic? Is it going to be martensitic? Just depends on what you've put into the mixture, into the alloy. So if we're looking at the periodic table, for the most part, and this is my version of the universe, so if there's somebody else out there that thinks there's other things we should talk about, all right. But for me, the majority of the metals or the elements that we care about, we're going to cover in the next 3 or 4 slides. We got iron and carbon, they make steel, right? Nickel, manganese, copper, cobalt, aluminum, titanium, vanadium, chromium, molybdenum, niobium, and silicon. These are a lot of the materials that we really care about in regards to the iron carbon diagram and how we alloy steels and some of the materials that we really care about. And I probably forgot a couple in here, but for the most part, these are the metals that we're going to be working with. Whether it's in the iron carbon steel zone of the universe, or if we're talking about using aluminum or titanium alloys. Or if we're talking about copper nickel alloys, or just nickel alloys. These are the things we care about in regards to welding and metallurgy. And we're not going to get off in the weeds and talk about cesium or something like that. These are the materials that we care about, and that's why we talk about chemistry and the periodic table. So then when we talk about gases, we're talking about helium, hydrogen, argon, nitrogen, oxygen, and carbon dioxide. Even though it isn't a element up here, it's a compound. It's carbon and 1 carbon and 2 oxygens. We care about that as a gas a lot of times in the iron carbon diagram. Steel welding universe, we'll use it as a shielding gas in conjunction with something like argon, or just pure carbon dioxide as a shielding gas for gas metal arc or MIG welding applications. So these are things that we care about. Another reason we care about chemistry is metals. If we're going to do gas tungsten arc welding, we're going to worry about tungsten, but you're not going to get very far talking about TIG welding, gas tungsten arc welding, without talking about tungsten, being alloyed with lanthanum or thorium or cerium or zirconium. It'll give you different electrical characteristics for welding with different materials. You know, we can use pure tungsten, but most of the time we're going to use tungsten that's been alloyed with another material such as lanthanum, thorium, cerium, or zirconium to give us better abilities to carry heat in the tungsten electrode, the non-consumable tungsten electrode, as well as the ability to conduct the electricity and give us an arc that is, better suited for our welding needs.
Alloying. An alloy is a mixture of two or more materials, at least one of which is a metal. Alloys can have a microstructure consisting of solid solutions where secondary atoms are introduced as substitutionals or interstitials in a crystal lattice. When a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form, called atom exchange and the interstitial mechanism. The relative size of each element in the mix plays a primary role in determining which mechanism will occur. Alloying. An alloy is a mixture of two or more materials, at least one of which is a metal. Alloys can have a microstructure consisting of solid solutions where secondary atoms are introduced as substitutionals or interstitials in a crystal lattice. When a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form, called atom exchange and the interstitial mechanism. The relative size of each element in the mix plays a primary role in determining which mechanism will occur. Alloying. An alloy is a mixture of two or more materials, at least one of which is a metal. Alloys can have a microstructure consisting of solid solutions where secondary atoms are introduced as substitutionals or interstitials in a crystal lattice. When a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form, called atom exchange and the interstitial mechanism. The relative size of each element in the mix plays a primary role in determining which mechanism will occur. Alloying. An alloy is a mixture of two or more materials, at least one of which is a metal. Alloys can have a microstructure consisting of solid solutions where secondary atoms are introduced as substitutionals or interstitials in a crystal lattice. When a molten metal is mixed with another substance, there are two mechanisms that can cause an alloy to form, called atom exchange and the interstitial mechanism. The relative size of each element in the mix plays a primary role in determining which mechanism will occur.
Alloying elements used in steel. Chromium. It increases resistance to corrosion and improves hardness, toughness, wear resistance, strength, and the responsiveness to heat treatment. Manganese. Manganese increases strength and responsiveness to heat treatment. Molybdenum increases toughness and improves the strength of steel at higher temperatures. Nickel increases strength, ductility, and toughness. Tungsten produces dense, fine grains, helps steel to retain its hardness and strength at high temperatures. Silicon improves the electrical quality of steel. Vanadium retards grain growth and improves toughness.
Here's another picture of some of the crystalline structures. You've got body-centered tetragonal unit. It's kind of a skewed guy over here on the left. You've got hexagonal close packed. You've got body-centered cubic, and you've got face-centered cubic. I usually try and give you guys a couple of different variations of the, any of these drawings, pictures, or concepts. There's a lot of good stuff out there in these Army manuals, so I cut and copy and paste and throw those out there for everybody to enjoy. Common characteristics of alloys. Alloys are usually stronger than pure metals, although they generally offer reduced electrical and thermal conductivity. Strength is the most important criterion by which many structural materials are judged. Therefore, alloys are used for engineering construction. Steel, probably the most common structural metal, is a good example of an alloy. It is an alloy of iron and carbon with other elements to give it certain desirable properties. Solid solution alloying. In solid solution, the elements are completely dissolved in each other, with the atoms of one element fitting into and forming parts of the space lattice of the other element. Figure 15.4 illustrates two ways in which solid solutions may exist. The atoms of one element may fit into the spaces between the atoms of another element, as indicated in figure 15.4, view B, or the atoms of one element may be replaced by the atoms of another element in the space lattice as indicated in 15.4 view A.
Aluminum. The chemical symbol for this element is Al. And the principal ore of aluminum is bauxite, which is produced by weathering of aluminum silicate rocks. Aluminum is a lightweight, soft, low-strength metal which can be easily cast, forged, machined, formed, and welded. It is suitable only in low-temperature applications, except when alloyed with specific elements. Uses. Aluminum is used as a deoxidizer and alloying agent in the manufacture of steel. Castings, pistons, torque converter pump housings, aircraft structures, railway cars, electrical transmission lines, and kitchen utensils are all made of aluminum. Capabilities. Aluminum can be cast, forged, machined, and welded. Chromium. The chemical symbol for chromium is Cr, and its ores are chromite and chrome ochre. I think that's how you pronounce it. Uses. Chromium is one of the most versatile and widely used alloys. It is used as an alloying agent in steel and cast iron, and in non-ferrous alloys of nickel, copper, aluminum, and cobalt. It is widely used in electroplating for appearance and wear, in powder metallurgy, and to make X-ray targets, mirrors, and stainless steel. Capability. Chromium is hard, brittle, corrosion resistant, and can be welded, machined, and forged. Limitations. Chromium is not resistant to hydrochloric acid, nor can it be used in the pure state because of its brittleness and difficulty to work. So chromium is very useful, but you just can't use it as chromium. You got to use it with something else. Chromium nickel, chromium iron, chromium copper, I think works, but you got to have chromium with something else. Cobalt. The chemical symbol for cobalt is Co, and the chief ores of cobalt are cobaltite and smaltite. Uses. Cobalt is mainly used as an alloying element in permanent and soft magnetic materials, high-speed tool bits and cutters, high-temperature creep-resisting alloys, cemented carbide tool bits and cutters. It is also used in making insoluble paint pigments and blue ceramic glazes. Capabilities. Cobalt can be welded, limited machinability, and cold drawn. Limitations. Cobalt must be machined with cemented carbide cutters. So you'll see a lot of cobalt show up in steels also. Manganese. The chemical symbol for manganese is MM, not to be confused with magnesium. Manganese is its own thing. And the chief ore of manganese is black manganese dioxide. Uses. Manganese is mainly used as an alloying agent in the manufacture of steel to increase its tensile strength. It is also added during the steel making process to remove sulfur as slag. Austenitic manganese steels are used for railroad track work, power shovel buckets, and rock crushers. Medium carbon manganese steels are used in the manufacture of car axles and gears. Capabilities. Manganese can be welded, machined, and cold worked. Limitations. Austenitic manganese steels are best machined with cemented carbide, cobalt, and high-speed cutters. I've seen this in a previous life in austenitic manganese steels in shovel buckets and rock crusher type mining applications where you need something that can really take a beating, and this stuff does it. So manganese alloyed steels are, like I said, they don't make railroad track items and power shovel items out of something that's going to be soft and malleable. So manganese alloyed steels. Molybdenum, also known as moly, because molybdenum is a mouthful to pronounce. Molybdenum is principally used as an alloying agent in steel to increase its strength, hardenability, and resistance to heat. Heating elements, switches, contacts, thermocouples, welding electrodes, and cathode ray tubes are made of molybdenum. Capabilities. Molybdenum can be swedged, rolled, drawn, or machined. Limitations. Molybdenum can only be welded in the atomic hydrogen arc or butt welded by resistance heating in a vacuum. It is attacked by nitric acid, hot sulfuric acid, and hot hydrochloric acid. So most of the places you're going to see molybdenum show up is as an alloying element in steel. Generally, it doesn't, show up as something's made of pure molybdenum. It increases the strength, hardenability, and resistance to heat. A lot of times you'll see molybdenum in applications where mining equipment, I'm pretty sure, and hardenability. Molybdenum I think it shows up in like excavator teeth and something like that where you can get work hardenability. Not sure. Don't take that one to the bank, but I thought I read something at one point about molybdenum showing up in those types of applications. Nickel. The chemical symbol for nickel is Ni. It was first extracted from a copper-colored mineral named Kupfer nickel. Today, it comes from sulfide, oxidized, and arsenical ores. Nickel is a grayish-white metal, very ductile and malleable. Uses. Most nickel is used in the production of ferrous and non-ferrous alloys. Chemical and food processing equipment, electrical resistance heating elements, ornamental trim, and parts subjected to elevated temperatures are all produced from nickel-containing metals. It is used as an alloying agent in the manufacture of stainless steel. Capabilities. Nickel alloys are readily welded by either the gas or arc methods. It can be machined, forged, cast, and easily formed. Nickel, you're going to see it they use it as an alloying element in steels. It shows up in stainless steels, and you can have nickel alloys such as the Inconel's, Hastelloys, and those other proprietary names of various product forms. And nickel alloys can be cast pretty easily. I worked at a place where we did some casting of nickel alloys. Seemed pretty easy, not easy, but they did it. But anyways, that's nickel. Titanium. Titanium is used as an alloying agent for aluminum, copper, magnesium, steel, nickel, and other metals. It is also used in making powder for pyrotechnics and in manufacture of turbine blades, aircraft firewalls, engine nacelles, frame assemblies, ammunition tracks, mortar base plates. Capabilities. Titanium can be machined at low and fast speeds, formed spot and seam welds, and fusion welded with an inert gas process such as gas tungsten arc welding. Limitation. Titanium has low impact strength, seizing tendencies, and low creep strength at elevated temperatures, above 800 degrees Fahrenheit. It can be cast into simple shapes only. Well, titanium is a pretty good material. It's pretty corrosion resistant. It's light and it's strong. It's got a lot of capabilities. So it's a little lighter than steel and a little heavier than aluminum, and it's pretty tricky to weld. But it's a good material if you need strength and weight. A lightweight material with a good strength. It's a good quality material that can be used in a lot of different ways. Tungsten. The chemical symbol for tungsten is W, and it is extracted in its pure form from wolframite or schistolite. It is hard, brittle, and non-magnetic and forms an oxide when heated in air. Uses. Tungsten is used in the manufacture of incandescent lamp filaments, and phonograph needles, and is an alloying agent in the production of non-consumable welding electrodes, armor plate, high-speed steel, and projectiles. Capabilities. Tungsten can be cold and hot drawn. Limitations. Tungsten is hard to machine and requires high temperatures for melting and is usually produced by powdered metallurgy sintering process. Zinc. Chemical symbol for zinc is Zn, and its principal ores are the sulfide blends, silicates such as willemite, and oxides such as franklite and zincite. Uses. The largest use of zinc is in the galvanizing industry for items such as pipe, tubing, sheet metal, and wire nails. It is also used as an alloying element in producing such alloys as brass, bronze, and in those alloys that are composed primarily of zinc itself. Capabilities. Zinc can be cast, cold worked, extruded, machined, and welded. Limitations. The use of zinc die casting in continuous contact with steam is not recommended. So zinc, you're going to use brass, bronze, and zinc alloys, and you're going to use it mainly as galvanizing, or you can use it as a sacrificial anode in corrosion resistant type applications.
Interstitial alloying. An interstitial alloy is an alloy that is formed when an atom of sufficiently small radius sits in an interstitial hole in a metal lattice. With the interstitial alloying mechanism, one atom is usually much smaller than the other, so cannot successfully replace an atom in the crystals of the base metal as happens with substitutional alloying. The smaller atoms become trapped in the spaces between the atoms in the crystal matrix called interstices. This is referred to as an interstitial alloy. Steel is an example of an interstitial alloy because the very small carbon atoms fit into the interstices of the iron matrix. Examples of small atoms are hydrogen, boron, carbon, and nitrogen. I look at this like gets back to my analogy about a pickup truck, and you got the back filled with soccer balls, and then you dump in a bunch of baseballs. The baseballs aren't going to replace the soccer balls. They're going to find a spot in between the soccer balls to hang out, live, do their thing. That's how carbon works in iron. Carbon isn't big enough to replace the iron atom, so it just finds a little hidey hole, an interstitial spot in between the bigger iron atoms. I'm sure metallurgists everywhere are cringing when I use the word hidey hole and tie it in with interstitial, but that's what happens. Substitutional alloying. Substitutional alloys are formed when two metallic components have similar atomic radii and chemical bonding characteristics, meaning the atoms are roughly the same size. Examples of substitutional alloys include bronze and brass, in which some of the copper atoms are substituted with either tin or zinc atoms. Another example is with metals silver and gold. These two metals form an alloy over the entire range of possible compositions. When two metals differ in radii by more than 15%, the solubility is limited. Solid solutions. Metal alloys contain at least two or more elements. Even pure metals typically contain some impurities. Two types of metal solutions. Substitutional solutions contain a solvent and a solute, where the solute occupies lattice sites of the solvent. Solid solutions. You can see the solid solution, which is substitutional. One atom takes the place of another that's pretty much its size. It would be like having a back of a pickup truck filled full of soccer balls, and you got 50 soccer balls in there. Well, you're not going to fit any more soccer balls in there unless you substitute something. Something's got to come out of there, and something's got to go in. So you take 25 soccer balls out, and you put 25 volleyballs back in there. They're about the same size. Not exactly, but plus or minus, they're pretty close. So you're substituting. That's what this copper nickel thing is about. Their atoms are about the same size. Well, let's say you have the same pickup truck, and it's got those same 50 soccer balls in the back of it. You can dump in another 50 softballs, and those softballs will find space in between the soccer balls. Those are interstitial sites. That's an interstitial solution. Interstitial solutions contain a solute that occupies non-lattice sites. The carbon doesn't replace the iron. It just finds a spot in between the iron atoms. Same as dumping all those softballs into the back of a pickup truck filled with soccer balls. They're not taking anybody's place. They're not the same size. They're finding a spot in between. So that's kind of how I think of this solid solution thing. One's taking its place and the other one's finding a hiding spot in between the bigger atoms. So in carbon iron diagrams in the carbon iron system, carbon is the small atom. It's like a softball. It finds a spot in between two soccer balls. So, or basketballs if you're a soccer hater, whatever. But that's the analogies I use. Copper and nickel both have an FCC crystal structure. That's why they can swap out. And then iron has a BCC structure, and carbon occupies the interstitial sites. This is a common arrangement in steels.
Questions, comments, or whatever. My name's Gary Pace. I'm a professional engineer, welding engineer, certified weld inspector. I'm out of Katy, Texas. There's my email address and my website. Feel free to drop me a line if you have questions or whatever. Want to chat about welding related or materials, or maybe you've got an idea on something I need to cover in a future episode. All right, take care. GP out.